for ICC passage number 5 in terms of highlighting. In the second paragraph, I highlighted that acids HXA, HXB, HXC, and HXD were volatile and acidic gases. In terms of anything else, you may have highlighted that the gas forms a solid because we know that that's an interesting sort of phase change. But I personally wouldn't have highlighted it. I would have just highlighted that thing about volatile acidic gases. And then we make note of table 1, which has got the results of the experiment. Question number 1 says, according to the experimental results, each of the 4 tested acidic gases has a greater what? Well, we can already eliminate B, because we know that any acidic gas is not going to be more basic than ammonia. So we can take out B. Now, according to the experimental results, these results tell us how far the gas traveled in a tube in a given amount of time, right? So we see that all of these are less than 15 centimeters. 15 centimeters would be the midway point in between. And we know that the distance traveled, speed of a gas, is directly proportional to the molecular weight, right? So we want to know a property that has to do with molecular weight, which says why ammonia would have traveled farther. So boiling point, it's got nothing to do with molecular weight, unless you're dealing with London dispersion forces, which in most cases we're not. Not in most cases, but in anything that's nonpolar, we're not. Basicity we can eliminate. We've already eliminated. Vapor pressure also has nothing to do with molecular weight. C, though, has a greater molecular weight than ammonia. These all have a greater molecular weight because they didn't travel as far as ammonia did, so ammonia was lighter, would have gone faster, traveled farther. C is our answer choice. 2 says the addition of which one of the following components to the saturated ammonia solution would have the least effect on the experiment. So let's look at what we got. HNO3, we know that that's nitric acid, that's a strong acid, probably not real likely to be our answer. I2 maybe, N2O5, NH4OH. Now, NH4OH looks interesting. And this is a way, you have to take these apart and see what they really mean. So A and C we can actually eliminate because they're the same answer choice. There's no way you'd be expected to know that, but N2O5, dinitrogen pentoxide, as soon as you put it in water, plus H2O, it turns immediately into 2HNO3, nitric acid. So there's no way we would have known that besides outside information, but A and C are actually cleverly disguised as the same answer. Same answer can't be right twice, so A and C are gone. Now between I2 and NH4OH. NH4OH, aqueous, is actually the exact same thing as aqueous ammonia. Basically NH3 plus H2O. So adding more ammonia to a saturated ammonia solution would have the least effect on our experiment, and we go with answer choice D. 3 says in the test, the NH3 solution was removed and replaced with a solution of saturated deuterated ammonia, ND3. As the experiment was then performed, an experiment was then performed with the acidic gas, and the solid ring formed at the D is equal to 15 centimeters mark. Which of the following could be the attested gas, acidic gas tested? So what happened? They reacted, they met at the 15 centimeter mark. That's right in the middle, so that means they must both have the same exact molecular weight. Now deuterated ammonia, deuterium is an isotope of hydrogen that's got 1 more neutron. So instead of a molar mass of 1 gram per mole, it's actually got a molar mass of 2 grams per mole. So ND3, instead of being 17 grams per mole, is actually 20 grams per mole. So we need something else that has 20 grams per mole. That eliminates A and C, so they both have different molecular weights, and we're left with HF or Ne, both of which are 20 grams per mole. We can eliminate D and go with B. Why? Because we needed an acidic gas. HF is an acidic gas. Neon is a noble gas, not an acidic gas. 4. Of the following, which term best describes the process where NH3 and HX react to make NH4X solid? So what happens in the tube? First you have NH3 gas, which reacts with HX gas, and that's going to form NH4. X gas. And ultimately, that gas is going to become NH4X solid. So what we had was a chemical reaction followed by a gas going directly to a solid, something we know is deposition. So we go with answer choice A, chemical deposition. Sublimation is the opposite process, of course. Anti-sublimation doesn't exist, and condensation doesn't apply because there's no mention of the liquid phase. 5 says, if the saturated ammonia solution were placed under a vacuum, i.e. if all the air were removed with a vacuum pump, what would be the effect on the ammonia? So if any of you guys have ever been in an orgo lab, one beyond your actual orgo lab class, because it's kind of low tech in there, there's something we use called a rotovaporator. And what a rotovaporator is what's the definition of boiling point? Well, we know that boiling point is when the vapor pressure equals atmospheric pressure. So if you take away all the atmospheric pressure, then the vapor pressure, whatever it is currently, has got a less of a rise, less that it has to go before it equals the atmospheric pressure and it boils. So let's say, just to illustrate that concept, let's say we have a substance that has a vapor pressure of, let's say 1. Let's say 0.1 atmospheres. So this is the vapor pressure of the substance. Well, usually we're at 1 atmosphere. So in order, we have to raise the temperature until the vapor pressure becomes 1 atmosphere, at which point it's going to boil. Well, let's say we put it in a vacuum and the new atmospheric pressure is 0.15 atmospheres. So it's a near vacuum. Now, we only have a very small distance to go up. So the boiling point is going to significantly lower. So if you screw with the atmospheric pressure, that has no effect on the actual vapor pressure of the ammonia solution. So A is eliminated. C, the pKb of ammonia would increase. The only thing that can affect a K, this is something we haven't covered yet, we're going to cover it in later lectures, the only thing that can affect a K value is temperature. We're not changing temperature, so C is also gone. D, the solubility of ammonia would increase. We know that with decreasing atmospheric pressure, for gases anyway, think about what happens when you open a bottle of soda. So solubility of gases, we know that if we heat up a liquid, solubility of solids and liquids increase with increasing temperature, because the hotter the liquid is, the more solute it'll take. This is also in a later lecture. As for gases, they follow an opposite trend. Increase solubility of gases with increased atmospheric pressure. And you can literally think of that as the pressure pushing the gas into the solution. Think about what happens when you open a bottle of soda, right? It has dissolved CO2 in it. That's why it's called carbonated. When we open the top of the 2-liter, that drops the atmospheric pressure. There's all of a sudden a much lower atmospheric pressure inside. What happens to the CO2? It fizzes up. It bottles out. It fizzes up out of our soda because it's not as soluble. So D is also incorrect, and that leaves us only with B. The boiling point of ammonia would decrease for this reason right here. Now 6 says ammonia is not an ideal gas, primarily because it experiences hydrogen bonding. Therefore, compared to the pressure and the volume depicted by the ideal gas law, which relation is true for 1 mole of ammonia at 300 Kelvin? Well, we learned that the ideal world is always greater than the real world, so the ideal pressure is going to be greater than the real pressure. Why is that? Because pressure results from the ammonia molecules colliding with the walls of the container and bouncing back, so it's that force over the area. So if they're attracted to each other, then they can't run as fast, they can't move as fast, and they can't slam into the wall as hard. So the more attracted to each other they are, the less the pressure is going to be inside. So the ideal pressure is greater than the real pressure. For volume, it's at 300 Kelvin. We know that gas molecules, we assume, have 0 volume relative to each other and relative to the volume of the container. So that's to say that in a container that's, let's say, 1 liter, the actual molecules of gas are so so very small that compared to the whole container, they take up almost no space. So we say that they have zero volume. But in actuality, they do have volume. So in PV equals nRT, the volume that we plug in for is the volume of the container, which for a 1 liter container, we just assume to be 1 liter. But is that how much space you actually have in that container? The answer is no, because the gas molecules take up space in and of themselves. So therefore, the ideal volume is going to be more than the real volume because those gas molecules actually do take up space. So we always remember that the ideal world is always greater than the real world, and we go with answer choice